a span of a set of vectors is the set of all linear combinations of them. For instance, given the set of vectors 1, 3, 0 and minus 1, 1, 0, the span of them will be the set of all possible combinations of them, meaning any number multiplied by 130 plus any number multiplied by minus 110, such that x and y are any numbers, any real numbers. So that means that the set spanned by these two vectors will be the set of, by doing the multiplication here and the addition, we can see that this is equal to the set, the vectors of this form, x minus y, comma, x multiplied by 3, right? That will be there 3x plus y, comma, and here will be 0 plus 0. So the vectors of this form such that x and y are real numbers. So any vector that is of this form, putting any x and any y number, will belong to the set spanned by these two vectors. Well, let's define now what is linear independence. This is going to be one of the most important concepts in linear algebra, the linear independence of several vectors. So we are going to say that a set of vectors is linearly independent, or Li, if none of its elements is a linear combination of the others. So none of the vectors in the set can be written as a linear combination of the others. If that happens, so then the vectors are independent. Otherwise, are linearly dependent. So, for instance, let's see if we have this set of vectors. 1, 3, 0, minus 1, 1, 0, and 0, 4, 0. So we can see that these vectors actually are not linearly independent, because it happens that there is some vector there that can be written as a linear combination of the others. So we can easily see that this vector actually can be written as a combination of these two. So you can see that 0, 4, 0 is actually equal to some number multiplied by 1, 3, 0 plus some other number multiplied by this. So we can easily see that these numbers here are actually 1, right? I mean, if you just put 1 times this vector and 1 times this vector, see what you get. You get 1 minus 1, that is 0, and then 3 plus 1, that is 4, and 0 plus 0, that is 0. So you can see that this linear combination, I mean, just putting here a 1 and here a 1, gives this third vector. So we did find one vector here that can be written as a linear combination of the other two. So that means that doesn't satisfy these conditions, and so because of that is not linearly independent, this set. So because of that, we can say that this set actually is linearly dependent, right? Because we are in the otherwise part here. Let's consider now this other set of vectors. Are these vectors linearly independent or dependent? In this case, it's not that clear if we can find some vector that can be written as a combination of the others. Well, in general, how do we find out if that happens? Well, we can see that to find the linear combination will be equivalent to say that really exists a number x that multiply by the first one and a number 1 that multiply by the second one and a number z multiplied by the third one, that we obtain the vector 0, 0, 0. So if these numbers x, y, and z exist, so then that will happen that any of these vectors can be written, putting in the other side, right? Can be written as a combination of the other two. Of course, I mean, if we put as x, y, and z the numbers 0, 0, 0, so this system has always solution. So, but we are trying to see if there exists some other numbers, I mean numbers other than 0, 0, 0. So in other words, we are trying to see if this system has a unique solution, I mean just 0, 0, 0, or has infinitely many solutions. So if this system has infinitely many solutions, so that will mean that there are some particular numbers here, non-zero numbers, such that one vector can be linear combination of the others, and then they will be linearly dependent. So we can translate then linear independence or linear dependence in terms of having infinitely many solutions or a unique solution. So it has a unique solution means that the vectors are Li. If this system has infinitely many solutions, so the vectors are Ld, are dependent, because we can find numbers x, y, z other than zeros such that this system has solutions. So, and this system, actually, we can write it as a matrix, right? So this system is equivalent to put these vectors just as columns. So we can put 1, 3, 0, minus 1, 1, 0, and 0, 0, 1. So if we write the matrix like this, x, y, z, so this matrix system is equivalent to this one. So all what we have to do is to find out if this system has infinitely many solutions or has a unique solution. Well, we have seen before that the system has a unique solution if and only if the determinant of this system is not zero. So let's find out what the determinant of this system is. So we expand this determinant by this row. That will be plus, minus, plus, minus, plus. So that will be just plus this minor here. So then will be then 1 minus 3, which is 4, which is not 0. So that means then that the system has a unique solution. That has a unique solution means that this system here has the solution only 0, 0, 0, meaning that there are no other numbers that makes this equation true. So in particular, we cannot put here numbers that are non-zero and so express one as combination of others. No, that's not possible. The only combination is when they are all zero. So that means that none of the elements, none of the vectors here is a linear combination of the others. And so because of that, these vectors are then linearly independent. Translate this the idea of vectors being independent to the idea of this equation has only the trivial solution. In other words, has a unique solution, and in case of a 3 by 3, we can say that determinant is not 0. We know now what means for a set of vectors to be linearly independent. So now we're going to say that is this set of vectors span some space V and are linearly independent, so we are going to say that this set of vectors is a basis for V. The cardinality of a basis is the dimension of the space. So we can say that 3 linear independent vectors are always a basis in R3. So if we have to decide these three vectors are a basis of R3, all what we have to decide if they are linearly independent, because we know that they will expand the whole set. Well, once that we have a basis, or in general, once that we have a set of vectors, we can determine if those vectors are orthogonal or not. So the idea of being orthogonal, we have studied before, and we know that two vectors are orthogonal if the dot product is 0. So a set of vectors is going to be called orthogonal if all the vectors, considering 2 by 2, right? This with this and this with this, all of them are perpendicular to each other. For example, is this set of vectors that we know already, we have proved already there was a basis, but is actually orthogonal? Well, in order to decide if it's orthogonal, we have to do all the dot products, this with this, this with this, this with this, and see if all of them are perpendicular. All the dot products are 0. So let's start. So let's calculate, for instance, the dot product of this with this. Remember that this is 1 times minus 1 plus 3 times 1 plus 0. So this is 2, which is not 0. So that means that already these two vectors are not perpendicular. That's it. So this set of vectors then is not orthogonal. So let's check if this set of vectors is orthogonal. So let's do the products. So let's start the product of this and this. So this is 2 minus 2 plus 0 is 0. So the first two are orthogonal. So let's consider now this times this. So let's do now this 0, 0, 3. So this is 0 plus 0 plus 0. So it's 0, 2. And then finally, let's consider this and this. So this is going to be 0 plus 0 plus 0. So it's also 0. So we can see that then this set is really an orthogonal set. One further step, we can say that a set of vectors is orthonormal if the set is orthogonal, as we proved before, as we showed before, but also the norm of each of the vectors is 1. So, in order to prove that a set is orthonormal, then we need to prove first that it's orthogonal, and then we have to prove that all the norms are 1. If the set is not, the set is orthogonal but is not orthonormal, so then we can normalize a set by just dividing by the norms. For instance, this set that we proved before that is orthogonal, we can see that it's not orthonormal, since the norm of each of these vectors is not 1. So if we want to normalize this set, we will need just to divide by the norms of each one. First, we need to calculate the norms of them. So the norm of the first one, for instance, is the square root of 4 plus 1 plus 0, right, will be the square root of 5. So the norm of the second one will be the square root of 1 plus 4, which is also the square root of 5. And the norm of the third one will be the square root of 9, which is 3. So we calculate the norms of each one, and then we divide by the norms. So the normalized set will be then the vector 2 over square root of 5, 1 over square root of 5, 0. And the other one will be 1 divided by its norm, that happen to be also square root of 5, and minus 2 divided by this 0, and then 0, 0, 1. 3 divided by 3. This set now is orthonormal. We normalize the set that we had before. So to normalize an orthogonal set is easy, just to divide by the norm. But sometimes we have given a basis that is not even orthogonal to start with. And so then we learn a more complicated process that will allow us to convert a basis, any basis, doesn't have to be orthogonal, any basis into an orthonormal one. To convert a basis, any basis, doesn't have to be orthogonal, into an orthonormal basis, we need to apply this algorithm that is going to be called the Gram-Schmidt process that will allow us to, from any basis, to obtain an orthonormal one. This algorithm consists in 2 steps. The first step, that will be this step here, will allow us from any basis to construct an orthogonal one. And then once that we have an orthogonal base, the B1, B3 until Bn, so then we are going to normalize, and then will be the orthonormal base. Okay, so the way to obtain that orthogonal base is first to consider as the first vector that we have given, u1. But the second vector, we are going to consider the second vector that we have given, but we are going to subtract a multiple of B1, a multiple of the one that we obtained before. And so on. We are going to keep doing that for all the vectors until we get to the vector number n. So let's start with this basis that we know already. We have is the one that we used before. We know that that was not orthogonal. So let's try to construct from this basis another one that it is orthogonal. So this is our given base. Let's say that we call this one u1, u2, u3. So our new base is going to be given then. V1 is going to be just u1, right? So this is going to be just whatever is our first vector. So it's going to be 1, 3, 0. And V2 is going to be our second vector, right? So the vector given here. Let's start by writing that one, minus 1, 1, 0. But we have to subtract here some multiple, we have to calculate this number, of B1. So let's start by calculating this multiple. The multiple, what we put in here, is the dot product of U2, this vector that we are talking about, the same one, this one, U2, times B1. Times this vector that we calculate here. So let's do the dot product of these two. So that will be minus 1 times 1 is minus 1, plus 1 times 3 is 3, plus 0. So this is the dot product of these two. And this is going to be divided by the norm of B1 square. I mean, by the norm of this one square. Well, the norm of this one, we can see easily that is a square root of 1 plus 9, right? It's a square root of 10. So the square of that is going to be just 10. So this is the number then that goes multiplying B1. And so now we put just times B1. And B1 is just this vector here. So this is 1, 3, 0. Okay, so let's do these multiplications here, and this will be then minus 1, 1, 0. And so here 3 minus 1 is 2. 2 over 10 is 1/5 times 1, 3, 0. And now we multiply 1/5 by this, and at the same time we can do the subtraction here. So let's do that. So we are going to have here minus 1 minus 1/5, comma, 1 minus 3/5, comma, 0. And now this is going to be now 5 times 1 is 5, so this is minus 5 minus 1 is minus 6 over 5. And here is 5 minus 3 is 2 over 5, 0. And so this is then how we obtain the vector B2 applying this formula. And for B3, we're going to do now all this operation. So for B3, we're going to write first U3. I mean, here we're going to write just the vector that we have given, right? This one here. So this is 0, 0, 2. And now we're going to do minus, and now is the multiplication, the dot product of that one, U3 times B1. I mean, the multiplication of these two. But when we multiply these two, we see that we have here 0, 0, 0. So the dot product of this is 0, right? So then this is 0, so we not even need to continue to do anything there because this is going to be the whole thing 0. So we keep going then, and so we put here minus. And now we do this part here. In order to do this part, we still consider U3, right? So will be this one here. But now it's times V2, I mean times this one here. So now it's the dot product of these two. Well, in the same way, the dot product here, we can observe that is 0, 0 plus 0. So it's going to be 0 also. So it's going to be 0 there. So B3 here, this is just then 0, 0, 2. And then we obtain, in this way, the third vector B3. So we are done with the step 1 of the algorithm. So the set that we obtain here, the set of these three vectors, V1, V2, and V3, are vectors that are orthogonal. And you should check that this vector, and this vector are orthogonal. I mean, when you do the dot product of two of them at a time, all of the dot products, all of them are 0. Okay, so we end up here then with a set of orthogonal vectors. So now we need to just to do the last step, that is going to be simple normalize them, which means just to divide each of the vectors by their norm. So then the first one, that is the 1, 3, 0, we know already that the norm, let me put it here, W1. So this is going to be 1, 3, 0 divided by its norm. So it's going to be 1 this times 1, 3, 0. So the vector is going to be 1 over square root of 10 and this. So that is W1. W2 is going to be this vector divided by its norm. So let's calculate the norm of this vector separately. The norm of B2 will be the square root of minus 6, 5 squared plus 2, 5 squared. So then this is square root of 36, 25 plus 4, 25, which is the square root of 40 divided the square root of 25. W2 then by, consider the vector B2 divided by its norm, right? Which means just multiply by the reciprocal of that. So then the vector is going to be minus, let's put 5 square root of 40 times minus 6, 5, comma, and so 5 square root of 40 times 2, 5, comma, and then 5 square root of 40 times 0. And so here is going to be just simplifying here. This is going to be minus 6 over this, comma, 2 over this, comma, 0. And we can, considering the 40, considering that the square root of 40 is actually 2, square root of 10, right? We can simplify a little further, and this will be just minus 3 over square root of 10, 1 square root of 10, 0. And that is then our vector W2. And finally, for W3, we'll have that is this vector divided its norm. So this is going, the norm is 2, so it's going to be just 0, 0, 1, right? So 2 divided by 2, which is 1. And this is then our set of vectors obtained after Gram-Schmidt process. So the first of the vectors is this vector here, W1. The second of the vectors, W2, is this vector here. And the third of the vectors, W3, is this one here.